Hi guys and welcome to Learn Extra Live Physical Science Grade 12. Thanks for joining in. I know a whole bunch of you have been watching right since the Grade 10 show. And as you can see, I'm Indiana and Phil is with me today. And Phil, want to tell us what we're chatting about today?
Absolutely. Okay, guys, today is very, very interactive, especially if you're sitting at a computer. Don't worry if you're not. If you're watching us, you can watch some of these simulations. I want you guys in on the reactions, and we're going to be dealing with rates of reactions today. It's a great lead up into next week's lesson, but rates of reactions is it, and we're going to be doing some online experiments.
Yeah, so guys, keep watching the Facebook page. I will be posting links and posts and all exciting things. Phil has some amazing things to show you, and I think it's going to be lots of fun. Phil, you take your spot at the at the board and let him get ready while I chat to you guys and let you know how to chat to me. Chat to me on facebook.com/learnextra, also on Twitter @learnextra. And I want to give a big shout out to Liberty. Thanks, guys, for making this awesome and making the show possible. So, guys, get chatting. Without further ado, we're going to go straight to Phil. Phil, take it away.
Thank you very much, Indiana. Okay, well, today we're talking about rates of reaction. Now, rates of reaction are not a very big part of your exams at the end of the year, but what I have done is I've noticed that rates of reaction is in every single final paper. It might not be worth a lot of marks, but it's usually the way that they teach or at least examine learning outcome 1. That's the way that they teach or learn or ask at least the experiments. They want to see if you can understand what an experiment will do when it's written on the paper. So what I've done is I've actually gone to the last 3 years of papers and I've actually taken little bits and pieces out of those exams. And I've asked Indiana to post a couple of those on the online, so keep watching the Facebook page. There's some links coming up. We're going to be doing some experiments together, and we're going to try to see if we can't get some of these things to become a little bit more clear to you. Okay, so what I'm going to talk you through is how rates of reactions work, what factors affect them, and how they're going to be asked in the final exams. Okay, well, let's get some of the definitions out of the way, some of the things that are particularly important. Okay, well, rates of reaction. Now, whenever I talk about the rates, now, here's something that I want to talk to you about. Okay, now, whenever I use the word rate, it's how fast or how quickly something is happening. Okay, now, there's two ways that we can describe this. So it's either how quickly reactants are used up, so how quickly they vanish or disappear, or how quickly products are made. And this is usually the way that they give you the questions. They tell you that a certain amount of product is being made in a certain amount of time. Now, this equation down at the bottom here is not something I'm going to expect you to learn, but one of the things that I want you to realize is that it's to do with a changing amount over a change in time. So now, if you were to start thinking about this in terms of practical terms, somebody said, how fast can you unpack the boxes out of a truck? Well, you'd measure how many boxes you can unpack and how much time it takes, and if you divide the two, you would get your rate. So your rate is how fast I can get a job done. Now, chemicals want to go from reactants into products, and this is going to measure how quickly that's going to happen. So just bear in mind that anytime I've got an amount over an amount of time, all I'm going to be talking about there is how fast the reaction is going. That is the rate of the reaction. Okay, so I hope that that's clear. Keep this equation in mind because we're going to use it in the next few slides. But what I'm going to do is I'm going to talk you through my challenge question, and Indy's going to be posting that up in a couple of moments. I want to talk you through, and it's actually one of the questions which I've seen in a past paper. It wasn't a government past paper, but I want to show you how they can ask this type of question. Okay, well, let's get to that challenge question. What I'm going to do is, there's a lot of reading and writing going up. I'm aware that you might not be able to see the sides, so what I'm actually going to do is I'm going to decrease the size of this a little bit so that everybody can see it, and it should fit nicely inside your screen there. And I've got a couple of options here. Okay, so it says an experiment is done 4 times. Which experiments are a fair test to each other? Now, I'm left with these 4 experiments where there's a whole bunch of conditions. Well, I've got my experiment 1, 2, 3, and 4. I've got differing temperatures, so there's 25 and 30 all the way through. And I've got differing concentrations. Now, those are measured in centimeters cubed. So experiment 1 was done at 0.05, and 0.1 for the next one. Okay, now remember that these might be moles or grams or whatever they might be. So maybe we should clarify that. Let's actually make that per centimeter cubed, because this can be grams or moles or whatever it might be. So you might see it as moles per centimeter cubed as a unit. But that's not the important part here. Now, another thing which we can change, or one of the variables which we can change, is the state of the zinc in this reaction. Now, remember that zinc is a solid. That's one of the clues. I can make it into granules, or I can make it into powder. Now, this is just a small snapshot of one of those papers. So what I'm going to be doing is offering you 4 options here: A, B, C, or D. Now, I'm going to ask Indy to be very, very careful about this. What I'm going to say is don't guess. Okay, you've got to explain why you're choosing A, B, C, or D. So what I'm going to say is that if you come up with an answer without an explanation, I'm going to tell Indy to ignore you. Because one of the things that's great on the page is I want you to come up with your answer, and your explanation is going to help teach others. So I want you to discuss this. So once she's got this up there, I want you to figure out, is it experiment 1 and 2 which are a fair test? Now, the operative word, or the words which I'm going to find important there, is a fair test. Now, if you guys don't know what a fair test is, I suggest you get on Google, you get on Mixit, you get on Twitter, you start asking about a fair test. Okay? There's a couple of options. Option A says, is it experiment 1 and 2? So I want you to look at the variables there. So that's one possibility. So let's just highlight it as we go. So is it experiment 1 and 2? So that's one option. Is it experiment 2 and 3? Now take a look at these variables. There's the next clue. So I've got to be able to identify whether or not 2 and 3 together are a fair test. What about option C? I can compare the results from experiment 2 and experiment 4. What about D, which suggests that we could compare the results of experiments 1 and 4? Well, I'm not entirely sure yet, but you guys are going to get hard at work on that. Indy's going to post it up on the page in a moment. She's also going to be linking up PhET, which is one of the experiments which I'm going to be doing on the board, and you guys can do this with me. So you can actually replicate the experiments. You can do them with me. It's very interactive. Okay, so let's get into the lesson today. How do I solve things like this? Where do I even begin? Some of you might have a clue. Some of you don't. That means you should get a pencil and paper and start taking some notes. Reminder that these are going to be posted up online for you a little bit later. Okay, now the part which I want to begin with, there we go. All right. First of all, I want to get into how do we measure how quickly a reaction is happening. The biggest problem is that I can't go into a chemical reaction and speak to the chemicals and say, hey, how fast are you reacting? Okay, this is a big problem. Okay, well, a couple of the ways that they can do this. I can measure the volume of a gas which is given off. I can measure the mass of a gas which is lost. Or I can look for a visual indicator. Sometimes there's a color change, or it becomes cloudy, or something like this. Now, you guys can try this experiment at home. Anytime you've got something which chemically reacts, if you've got a fizzy tablet, one of the things that you can do is drop this into water. Now, this is one of the easiest experiments that you can do. If I take that fizzy tablet and I drop it into a glass full of water, it dissolves, and there's a visual indicator that the tablet has dissolved. It's finished its chemical reaction. All the bubbles have gone. Now, you can tell how fast that reaction has taken place by measuring it with a stopwatch. Okay, but even cooler than that, we're going to be doing a couple of experiments on the board. So, how did they ask these 3 inside exams? Well, I'm not entirely sure, and somebody last week said, okay, please, 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 some of the diagrams are so complicated, and these guys at home are busy scribbling these really interesting pieces of scientific apparatus. I'm actually going to ask Indy to post those pictures up online. You should start seeing them come up online. There's one picture which has got like a Erlenmeyer flask, and there's one with the scale, and the ones which I post here, you're going to see there fairly soon. I'm just checking with Indy. Is that managing to get online?
Yes, it is.
Absolutely fantastic. Okay, the first of our very complicated diagrams is up on the board here. Okay, now I'm going to run you through this very, very slowly, okay, so you can inspect that diagram for yourself. Okay, this is the one is to do with the volume of gas which is delivered. Now, let me just go through this diagram. Okay, I've got a conical flask or an Erlenmeyer flask on the left-hand side here. And this is this really nice sort of triangular thing on the side here. Now, this is a side view. I'm looking from the side of this experiment, and there's a reaction which is happening inside here. And this is the same reaction which I described to you. I've got a fizzy tablet Now you can try this with a grandpa tablet or whatever might be the case. Now as long as it makes fizz, as long as it makes bubbles, I can try this experiment. Now one of the best and most accurate way that you can actually measure the rate of the reaction is I can actually see how much gas is coming off. Now those bubbles, remember, are going to be carbon dioxide. There is a gas which is coming off here. So there we go. So carbon dioxide is one of those gases which can come off. And a great thing about this experiment is I've got a rubber stopper over here, and that rubber stopper is allowing all that gas to go into one place. That rubber stopper is telling me that all the gas must go inside the syringe. So the gas is going to go inside here. So I've got CO2, which is now being trapped inside a syringe, so I can measure exactly how much is coming out. Now remember that when the reaction is going to proceed, so inside my flask over here, it's going to enter my syringe over here, and this is going to go backwards. There's another piece of apparatus over here, which I really want to bring attention to. I need to measure an amount, and I need to measure time. Okay, so here is our stopwatch, and the stopwatch is a very important piece of information to know. They might actually ask you to design an experiment like this. So, what would I need? I need a flask, I need a rubber stopper, and I need a syringe over here. I'm not sure if you can see that label, so what I'm going to do is I'm going to write it on top here. So there is a syringe, just like the one you get an injection from, but the great thing about this is it's not going into my arm, the gas is going inside the syringe. Okay, so all of this is to measure the amount of gas which is coming off. Now that's not enough. I don't want to know how much gas is coming off unless I can measure how fast it's happening. Because remember, we're after the rate. Now the really cool thing about this is you can actually plot this on a graph. So let's take a look at that graph. I've actually plotted one for you. Okay, there it is. Now the amount of CO2 which is coming off here. Let's just keep our labels here. I actually want you to draw this with me. So I've got CO2, I'm measuring the amount of volume as time goes by. Now there's something I want you to notice about this graph. It becomes flat. Okay, so there's a few pieces involved here. Remember that I'm measuring amount and I'm measuring time, and that the rate itself is equal to the amount over the time. So what I can actually do is I can measure the change in the volume over the change in time. Now, if you've done grade 10 maths, and if you're in matric, I'm hoping that's true, you can actually figure out that this is a change in y over a change in x. So the rate is equal to the slope of the graph. Now that's quite important. Okay, I can actually figure out how fast my reaction is taking place because of the way that my graph is shaped and which way it's pointing. So what I'm going to do is I'm going to put a few arrows onto this graph, and we're going to see what the slope is in those places. So let's choose a different color there. So what I'm going to say is that right at the beginning, there's too many arrows there. Hang on, there we go. So at the moment, right at the beginning, I can see that there is a very steep slope. The slope is high. So what I'm going to say for that one is that the reaction is very, very fast. Okay, but now before I say that, let's say why we say that. I can see that there is a steep slope. There we go. So it's very, very steep. I can see that the graph is going up very, very quickly, and that is a steep slope. That's what I'm saying in my answer there. Therefore, I can say that there is a fast rate. Okay, that means that the reaction is happening very quickly. I'm getting a lot of volume for a very small amount of time. Okay, but now what we're going to do is we're going to move over to this next part. I'm going to draw in a new arrow. So let's draw in a yellow arrow over here, and let's see what happens there. I hope that you can see that. It looks like my producers put it up on the screen for you, and I need to figure out what's going over there. When I've got a slope which looks that way, I know that there is a zero slope. What does that mean? A zero slope means that the reaction has stopped in this case. The reaction is no longer happening. Why? Because my slope is zero. That means that my reaction rate is also zero. So there is no rate. There is zero rate happening over here. It is a very slow reaction. It's slowed down. You can see that the graph is getting flatter and flatter and flatter. till eventually it runs out of tablet and it stops, and then you drink it. Okay, I don't recommend drinking anything out of lab equipment. We're all about safety here, so please, no drinking out of this lab equipment. Even if it is a fizzy tablet and it's a vitamin or whatever, please don't do that. Syringe is not for medicine either. This is a gas syringe. Okay, well, that's one of the methods that I can measure the rate of reaction. I can measure the volume inside one of these, and I can measure the time with a stopwatch. How else can I measure the rate of reaction? Well, I mentioned two more ways. Well, this is the other way, and this is another one of those pictures which is going up on the page. Okay, this one's quite easy. I can actually measure how much of my experiment is disappearing. So the first one says the mass of gas which is lost. Now remember that some of these reactions are producing gases. And if I label this one, this particular one, if you were watching Bruce's lesson, you saw that hydrochloric acid was an acid. If I add that to calcium carbonate, which is chalk, if I add a base to an acid, what I'm going to get is a salt. And in this case, I'm also lucky, I'm going to produce bubbles. And this is the same way that bubbles are made inside those fizzy tablets. Inside those fizzy tablets, I'm producing CO2. That is carbon dioxide, and importantly, that is a gas. Now take a look at our reaction. In this picture, I can see that there's a beaker which is filled up with liquid, but a gas is going to escape. So what's going to happen is that CO2 is lost. Now, it might not seem like it, but even gases have got mass. A gas has mass. Okay, so what sort of graph might I expect if I take a look at the reading down here at the bottom? A lot of you don't know what this thing down at the bottom here is. This is a mass balance. Okay, now a mass balance is almost exactly the same thing that you can stand on to measure your mass or your weight. So a mass balance, this is something to measure how much mass is inside the experiment. A mass balance is a very important thing inside the lab, and it usually gives me measurements inside grams, and I can actually figure out what's going on in this experiment just by looking at the mass. At the beginning, I haven't lost anything. But what I'm going to find is that as I lose CO2 into the atmosphere, it's going to be carried away, and it's no longer resting on that mass balance. So this mass is going to decrease and decrease and decrease. Okay, this one is going to feature a little bit later, but let's hang on. Let's figure out what sort of graph I can expect here. This is a slightly different graph. I've plotted mass in grams versus time. So what you'll notice is that the mass is going down as we see time passing on. Now, once again, if I take a look at the rate at the beginning, or the slope of my graph at the beginning and the slope at the end, what you'll notice is that the slope is doing exactly the same thing, except it's in reverse. Okay? At the beginning, I've got a very steep slope. That means that the line is very close to vertical. That means that my rate is very high. That's what I can tell from this graph. So I can tell that my rate is high because the slope is very, very steep. What about the rest of the graph? What I can see is that the graph is going to flatten out. I can see that the graph has indicated that the reaction has stopped. So there we go. So my reaction has stopped. Now be very, very careful. If you're studying equilibrium, please don't get these two mixed up, because a flat graph over there can mean something completely different. Look at your graph. Mass versus time. Is this a rates question or an equilibrium question? Next week, if you join us, I'm going to show you how to tell the difference between the two. Okay, well, we're on to our third type of measurement. So what I can see over here is that I can measure my slope, and that can tell me how fast my reaction is going to take place. Well, the thing is, at home, you're not going to sit with this fancy equipment. I'm not going to watch my experiments on a scale. I'm not going to put my fizzy tablets on a scale and then measure and then measure and then measure and write down my results. The one thing that you're going to notice is that this mass balance is very, very precise. It can measure to 2 decimal places, which your scale at home cannot. So this is a very difficult experiment to do at home. Now, it's way, way easier to just look at an experiment and tell if it's done, if it's finished. Okay? So a visual indicator is something which I can see with my eyes. Now, you can see this over here. We've got another flask over here. And I've got two things which I've got mixed inside there. I've got sodium thiosulfate. So if you want to do a little bit of a search inside your textbook there, let me label that. This stuff is called sodium thiosulfate. And strangely enough, it's actually used inside some foods to preserve those foods. So sodium thiosulfate sometimes has got a little bit of a burny taste, but it keeps stuff fresh for a very, very long time. Sodium thiosulfate is the stuff for the job, except hydrochloric acid is not going to be your friend if you're trying to do that. Okay, so hydrochloric acid and sodium thiosulfate, these go together to make a product which I can actually see. Okay, well, let's take a look at my beaker over here. Well, this is actually a flask, sorry. You can do this with a small beaker as well. And what you'll notice is that there's a cross underneath there. This is another one of those pictures I've asked Indy to post up on the page. Managed to do that?
Posted already.
Fantastic. Okay, so you guys have got those 3 pictures. You're making notes on these, I'm hoping. I can see that there's a cross which is happening down here, right down at the bottom. That cross is drawn on white paper down at the bottom here. So if I had a nice sheet of white paper, I would draw a cross on it, and I will put my flask and my experiment on top of it. Now, what you're going to notice is that as the experiment happens, these two are going to make a solid. Now, if I look at my diagram here, I've got a liquid, aqueous. I've got aqueous. That means that I've got a liquid at the moment. So if I start producing a solid, what I'll start noticing is that I can no longer see through there. And as the experiment goes on, I'm going to find that I cannot see the cross anymore. So the minute that happens, or at least the second that that happens, I need to stop the stopwatch. And this is the experiment which I'm going to be asking you. If you've got access to the Department of Education final papers, the 2010 paper, question 6, I'm actually going to be running through it, and it's a fantastic example of how to use this method. So once again, a visual indicator tells me that the experiment is finished by how it looks. Now, in this case, the cross is going to disappear. I'm changing a liquid into a solid, and I can actually see that. That's when I stop the stopwatch. Okay, well, I'm hoping that people have absorbed this. They're busy with a challenge question. I think it's time for an ad break. What do you think, Indy?
Sure, I think that's a very good time for an ad break, guys. I see that there's lots of questions on the page. I'll ask Phil now during the break, and keep them coming. Also remember just to make sure they are relating to the topic that we have been going over. So without further ado, let's go to a little break. See you right now. Hi guys, and welcome back, grade 12 Mindsetters. Welcome back to Learn Extra Live. This is physical science. I just got to give you a little push. When it gets back to Phil, he's going to go over a really amazing site, which I am about to post for you. It's got interactive simulations. It's called PhET, and Phil is going to tell you more about it. I will be putting it onto the Facebook page. So if you guys are using PCs, please go and check it out. If not, maybe you've got computers at school, so maybe it's worth saving the link and having a look at it later. Also, grade 12s, let us know if you're watching. We are nearing 10,000 Mindsetters on the page, Phil. I just had to give a little shout out about that. I'm hoping that we get them tomorrow, though. I'm pretty confident. What do you think?
Absolutely. Okay, 10,000 is very, very close. Tell your friends, tell your teachers to tell your friends.
200 away, literally 100 and something away.
Absolutely, we're doing so well. It's looking really, really fantastic on the page. And I've been watching you guys. You really are amazing. You help each other so much. And one of the awesome things is that you actually share your answers and help each other out. It's like having your own personal tutor. I know that tutors are really expensive, but you guys are amazing. As soon as one person knows the answer, they help all the rest out, and that's what it's all about. Okay, well, helping you guys out. Now, I want you guys, if you can't get this yourself, try and get to a PC which has got some internet access on it, because this program is amazing. It's free, and that's the fantastic thing about it. Okay, now I've talked about this on previous shows before, but this is basically a science lab on your computer screen. And I actually want you to play around with this and see if you can't figure out what's going on in these experiments. Now, the thing that amazes me about this program is I can actually do the experiments on my screen using my mouse. Now, lucky for us in the studio here, I can just touch the screen and we can play around with the chemicals. Now, the box on the left here, what I'm going to be talking to you about, where my cursor is over here, I can actually take a look at these chemicals at a microscopic level. Now, this particular picture actually allows me to play around with these collisions. Now, I started to talk to you about what's happening at a microscopic level, but we haven't actually sort of figured out how can I affect the way that things interact at a microscopic level. Well, we're going to start to get a little bit of a clue from this. Now, just to give you a little bit of a hint as to how we explain all of rates, I actually start to take a look at some of the words here. It starts to talk about single and many collisions. Now, let's just give you an idea as to how this actually happens. I've got 3 particles inside that box at the moment. I've got a yellow one, I've got a purple one, and I've got a blue one. Now, you can see the reaction right at the bottom of the screen. I can see that A plus BC, so that means a yellow ball plus a purple ball and a blue ball actually go to give me different chemicals. A is going to join on to B, and C is going to go off on its own. So what I'm going to show you is forward and reverse reactions here. Now, this is not equilibrium at the moment, but what I'm going to show you is how reactions actually take place microscopically. Now, the cool thing about this is I'm actually going to show you, and I hope my producer shows you this at home. Okay, so let's try to see if we can make that a little bit bigger. Okay, there we go. And what we're going to do is I'm going to show you what's happening microscopically. I can actually pull this just as I would a normal spring and actually pull it back and get that yellow ball to move backwards and forward. And what you'll actually notice is that microscopically, reactions are taking place. I'm changing the partners microscopically, and this is what's happening every time reactions take place. So I hope that you can see on the right-hand side, we can actually change what goes on microscopically by changing some of these things. So what I'm going to do is I'm going to reset that, do it again. So we just say yes over there, and we're going to do this again. I want you to watch very carefully. At the moment, I've got 0 energy inside my system. The reaction can't happen because the 2 particles are separate. So I want you to picture, well, these are reactants. These are chemicals which want to get together. The only way that I can get them together is to give them energy. So that's what I'm going to do. I'm going to take my finger and I'm going to give a little bit of energy to my reaction. So I want you to watch on the left of your screen so you can actually see that I pull the spring over here, I pull it backwards, fantastic, and then I release it to give all the energy. And you can see on the right-hand side, it actually tells me that my total energy has gone up. So I release. And what happens is I actually get the reaction taking place. So now I've got a single yellow, and then I've got a single blue, right? And it actually happens very, very quickly. Now, if you can picture this happening tens of thousands of times a second, that's really fantastic. And what we're going to do is we're going to shift our attention to another experiment over here, which is called the rate experiment. Now, it's the same box, but what we're going to be able to do is we can actually tell how much energy is inside the experiment. We can tell how fast the reaction is taking place. We can see what's going on microscopically, and that's fantastic. So I want you to go find this simulation. It's called Reactions and Rates. Reactions and Rates is one of those simulations inside that fantastic site. Okay? So what I'm going to do is I'm going to ask Indy just to give you a little bit of a heads up there. So it's Reactions and Rates inside that PhET program.
What I might even do is post the exact link. That's exactly what I'm going to do,
That's
guys.
amazing.
Yeah.
Okay, so
Yeah.
Indy is an amazing helper, and she's helping you guys. Okay?
Done.
So a big thank you to Indy. What we're going to do is we're going to go back to our lesson over here, and we're going to figure out why this all happens. So we figured out 3 different ways to measure our reaction rate. Now, how do we actually explain what's gone on? Well, I mixed 2 things inside a jar, and it just went, and it looks like milk. Now, you might say, okay, well, how am I going to try and figure out how to affect this? I don't have any control of the individual atoms inside there. So what I'm going to do is I'm going to start taking a look at ways in which I can change how quickly these things happen. Well, let's start taking a look at some of the things which might actually change a reaction rate. Now, these are the main 5 factors which happen, and I'm going to ask my producer to put them up on the screen there for you. And what I'm going to see is that they affect different things in different ways. Now, if I have a solid, now I can't emphasize this enough. You can't just go into your exam and say, okay, well, surface area. Some things don't have a surface area. Liquids and gases, generally, you don't describe that they have a surface area. The thing which is affected the most over here is that solids. There we go. Solids are the things which are affected by a change in surface area. Concentration is something which happens mostly to solutions, sometimes liquids as well. There are exceptions to this, but now concentration is something that I usually talk about when I'm talking about the solutions. Now, when I'm talking about gases, I can talk about the pressure. And the one nice thing is all 3 of these first things are going to affect the reaction in exactly the same way. If I have more surface area, reaction goes faster. More concentration, faster reaction. More pressure, faster reaction. And temperature applies the same way. What I'm going to find is that temperature affects all reactions. Now, one of the things that I'm going to notice is that temperature is probably the most important factor inside a chemical reaction. Now, temperature is something that you can actually measure this at home. Now, remember I told you about that experiment where you got that fizzy tablet? I want you to put one inside a cold glass of water and one inside a hot glass of water. You'll actually notice that the temperature has a very big effect on the way that that thing dissolves. The faster it goes is because a higher temperature has come in from there. So, all of these factors are going to increase the rate of reaction. The very last one is a strange one, a catalyst. Now, a catalyst itself, if we're making notes on that, a catalyst itself can be very easily misunderstood. A catalyst is a chemical which helps the reaction, a chemical which speeds up the reaction without being changed. So it helps without changing. Now that's quite important. So if it helps without changing, I can call that chemical a catalyst. Now, a lot of people might say that anything which you add, which speeds up the reaction, is a catalyst, but that's not necessarily true. I've got to make sure that it does not change throughout my experiment. Okay, so let's just run through these again. Okay, my first factor when I've got a solid is the surface area. Now, surface area is something very difficult to understand. If I've got this pen, it's got a certain surface area, but what you'll notice is that anything which is solid has got atoms inside it which are hidden away. If I want to react with the outside of this object, I can only touch the outside. But when I open it up, what I'll find is that I can go inside that object. So the surface area has been increased in that way. So if I open up the object, I find that I've got more access, I can find my way inside that object, and that means that I can react much, much faster. So exactly the same way as you can start to think about, let's say, a box of biscuits. This is the way that I explain it. If I just open the top of a box of biscuits, I can only take from the top. I can only take out one biscuit at a time. But if I take the biscuits out on a plate, I've exposed more of those biscuits and everybody can take. And that way, the rate at which the biscuits disappear off the table is going very, very quickly. So I've opened up that object, I opened up that packet, and what I found was that my surface area increased the rate at which the biscuits were eaten. Okay, now concentration is a little bit more of a difficult one. Now, one of the things that you can actually figure out is that concentration affects reactions in exactly the same way. Now, I will find that a higher concentration means that the reaction can happen faster, but why? Well, all of these things are going to require a little bit more of an explanation. Now, when you explain in exams, here's something particularly important. Okay, how do I explain what controls chemical rates of reactions? Well, I need to use the following two words, and these two words are going to be very, very important. To have a reaction, I must have what's known as effective collisions. Okay? So effective collisions are what cause chemical reactions. So let's actually make that as a note. So effective collisions control the rate. Okay, well, what are these effective collisions? Well, effective collisions result in a reaction. So effective collisions make a reaction. That's really important. Now, when I use the word effective collision, that means that a reaction has been successful. I've actually performed a reaction. Now, one of the things that I'd actually like you to do is for these three requirements for an effective collision, I actually want you to get a key and I want you to get a lock inside your hand. Now, what you can do is you can picture the key and the lock as reactants. The product is the key inside the lock, which is now opened. So let's try to figure out how we're going to open up this lock. Now, this might sound a little bit silly, but what you're going to find is that you need an effective collision between the key and the lock to open it up. Now, I know that just putting a key and a lock anywhere inside the room is not going to get that lock to open. So having a key and having a lock doesn't mean that that lock is going to open. So the first requirement, and this might sound a little bit strange, for an effective collision, well, let's slide it down. Let's figure it out. The particles must collide with one another. They must actually meet each other. The key must find the lock. So what we'll find is that objects which do not collide cannot react. And you might say, okay, well, that's a little bit silly. To have an effective collision, I must have a collision, but it's quite important that you actually note that the chemicals must find each other. Okay, so they must collide with each other. Okay, well, let's say I've got a key and I've got a lock, and I decide to just sort of fiddle around with this key. I'm not going to unlock that lock. The second requirement is that I must give it enough energy to go inside that lock. Now, there's one other and very, very important thing, is that because chemicals have got a good side and they've got a bad side. You know how you want a photograph taken of your good side? Okay, chemicals have got a good side. Now, if you want to talk to me, I want you to come to my face and I want you to talk to me. I don't want you to walk behind me. Chemicals are exactly the same way. For them to shake hands and to make a deal, they must be face to face with each other. They must have the correct orientation. Now, these three requirements are all changed when we change those other factors. So let's run through these very, very slowly. Okay, the first thing which I need for an effective collision, absolutely, I need them to collide. Okay, we've actually just made a line we're meant to be highlighting. There we go. Aha. All right, so they need to collide with one another. Fantastic. The other thing which they need is energy. You need to be able to push that key inside that lock, and that's very, very important. Okay, and then the last requirement is they must meet each other at the correct angle. They must meet each other face to face with the correct orientation. And that's a very, very important thing to note. That's fantastic. Okay, so first I need a collision, second I need energy, and the third thing I need is the correct orientation. Now I'm going to give you a little bit of homework. I want you to go back to these 5 factors, and I want you to explain how these are going to change the effective collisions. So if I have more surface area, to give you an example, what's going to happen is there's going to be more space to collide. So there's more chance of a effective collision. The reaction rate will increase. So I want you to run through all 5 of these and explain it in terms of effective collisions. So take these 3 and say, okay, well, if I'm changing the temperature, what am I changing? Well, microscopically, let's take a look. What I'm going to do is, for those of you that have got FET at home, fantastic. For those of you that don't, get to a computer soon, just save the link. Indy's posted up on the page and you can follow it. Okay, here it is. Okay, now we are going to do our online experiment. You guys are going to do this experiment with me. On the right-hand side, what I can actually do is I can actually change how many reactants I put inside. So what I'm going to see is that, well, I decide that I want to have a few particles of A, so I'm going to increase that. I've got, let's say, 4 A particles. Now, A is going to react with a chemical called BC, which is a purple and a blue one. So let's put some of those in as well. So I start my experiment with 4 of each of these. Now, as I begin my experiment, what I'll notice is that they are bumping into each other. So the first requirement for an effective collision is being met. I can see that A, which is the yellow ones, is colliding with BC, which is the purple and the blue ones, and they're just flying around. They are cooperating with each other. Nothing is happening yet. So what I can see is that my yellow dots and my blue and purple dots, nothing is changing. No reactions are taking place. Okay, well, the question is, why is there no reaction? Well, one of the things that I notice over here is that my total average energy over here on my energy graph is not meeting something. Now, if you remember from grade 11 chemistry, this is a graph which shows me an endothermic reaction. So on the left, I've got A plus BC over here with my reaction coordinates over here, and it goes towards AB plus C. So that's my products. My total average energy needs to match the activation energy. Now here's the cool thing. I want you to watch what happens inside the box once I increase the temperature. So that's the first thing which I'm going to do. We're going to try get a reaction to take place with extra temperature. So watch as I raise the temperature over here. I'm going to increase my temperature. Watch what happens to the particles. The particles are starting to move a little bit faster, but still no reaction. So let's do that again. I'm going to raise the temperature. You can see the fire. And what we'll notice is that the average energy is now much, much higher than it was before. So the particles are starting to get excited. So temperature is one of the major factors. When temperature increases, I increase the total energy of the particles. Let's heat it up again. And what you'll actually notice is that as soon as I've gone over this initial part, what you'll actually start to see is I've made new molecules. I can actually see over here that I've made a new molecule, which is one yellow, one purple. And what I'm actually seeing is that I've got differing amounts over here. On the right-hand side, I can actually see how much of each is taking place. Now, what I can actually do is I can start to put in more of one of the particles, and we can try to see if we can't change this experiment. This is the amazing thing. I want you to play around with this. Now, I've got a pump over here to put in more of one of the chemicals. Let's actually take a look. What happens if I start introducing lots of one? In other words, increasing the concentration of only one of them. What I'll actually notice is that as I pump this, I'm actually releasing more particles of A inside there. Now you can see that there's lots of yellow. Now what you can see is that I've increased the concentration of my yellow. So that is particle A. That means that the rate of one of the reactions is going to be increased because there's more collisions, there's more chance that there's correct orientation. That means more successful collisions and a faster rate. Okay, so what I did there was to increase the rate of reaction is I got lots of these to happen. Okay, well, you can experiment. Some of the things which you can change is you can make a hot or a cold experiment. I can make lots of concentration, or I can make very little. Okay, but what I'm going to do is I'm going to slow things down a little bit. I'm sure that most of you are just watching these particles flying around on your screen. Okay, I want you to figure out how you can actually change the rate of these reactions. This is a great experiment. I'm going to be using it next week as well to explain equilibrium. Now you'll notice on the right-hand side that I've made a lot of A, which means that I've got very little BC left over. I've got 10 A particles, and I've only got one BC. The reason that that's happening is because there's so much A, it reacts with the BC very quickly. And you can see the numbers changing. I've got 11 and 2 and 2. That's going to change as the experiment goes on. So I'm just going to end the experiment for the moment. And what we're going to do is we're going to go back and try and figure out how do I actually get asked this. This is not going to happen in your exams. Once we come back from a short ad break, I'm going to show you exactly how it was asked in 2010. What do you think, Indy?
I think that sounds fantastic. Okay, guys, please, we're going to take a quick break, and don't forget that we are giving away a Casio calculator for today's lesson for the best post or for the best person who interacts the most, answers the most questions, tells a joke, I don't know, anything like that. So what we'll do, take a short break, and we'll see you now shortly. Bye. Hi guys, and welcome back to Learning Extra Live. I didn't actually realize we have 15 minutes left to the show. That's how much fun we were having. And Dile thought that your animation was amazing and everyone was loving the lesson, Phil. So well done for an awesome lesson. But before I give it back to Phil, because I know that he's just going to talk a lot, and which is rightfully so because he's the teacher and he should be running the show, not me. I just wanted to let you know, guys, we are also giving away a labeler. But that's one labeler per day through grade 10, 11, and 12 to the person who interacts the most. So guys, keep watching your page for that announcement. Tomorrow, we've also announced the winners of yesterday's Casio calculator, so please check to see if you are one of those lucky winners so you can email your postal Addy off. Okay, so Phil, let's do it. We've got a few questions. Where would you like to start? Would you like to finish?
Well, what I'm going to do is, because we're short on time, I'm going to put some people out of their misery and actually help them through the challenge question.
That's a good idea. That's why I asked you.
Absolutely. And then we're going to help a couple of the curious callers who are talking about, they're wondering about energy. We're going to answer some of those questions.
Awesome. So take it away.
Absolutely. Okay. Well, let's put you out of your misery. Which one of these was a fair test? Could I compare 1 and 2? Could I compare 2 and 3? Could I compare 2 and 4 or 1 and 4? Okay. What I'm going to do is I'm going to run you through some of these. Now, to give you a little bit of a clue as to what a fair test is, I can only change one variable at a time. That means that only one thing can change from one thing to the next to make it a fair test. Some of you are posting the correct answers, so I actually want to run through these answers and just see what's a possibility. Okay, well, let's try see if we can compare 1 and 2. if I look at experiment 1, it's got a temperature of 25. Experiment 2's got a temperature of 30. Okay, so temperature has changed. But I see that I've also changed the concentration and I've changed the state of zinc. So it cannot be option A. I changed everything from 1 to 2. Okay, well, let's take 2 to 3. Okay, well, from experiment 2 to experiment 3, I changed the temperature. I kept the concentration the same, but, and here's the but, I changed from powder to granules. So I changed 2 things. This is not a fair test. So I can see that A and B are not fair tests. I cannot compare 1 and 2, compare 2 and 3. That is not fair. But one of the things that I can do is take a look at experiment 2 and 4. Experiment 2, and I'm going to highlight them as I go. Experiment 2 had a temperature of 30. So that's the same. Okay? Experiment 2 had a concentration of 0.1, and experiment 4 changed the concentration. There it is. So that was changed. The really cool thing about this is that I kept the state of zinc the same. That means that this is a fair test. Okay? So I can actually see that experiment 2 and 4 are fair. I can see that the explanation over here is that only the concentration changed. So only concentration was changed. Okay, so square brackets mean concentration. For those of you that don't know, I'm just trying to make a point here. So only concentration changed, and that made that the fair test. Now, it's quite important when you make a fair test that you only change one variable. Otherwise, it's not a proper scientific experiment. Let's just make sure that option D is not possible. Okay, well, in experiment 1, my temperature was 25. Experiment 4, it changed. Okay, so temperature has already changed. If 1 and 4 are a fair test together, then I must keep everything else the same. But everything falls apart. Look, the concentration is changing from 0.5 to 0.2. Okay, already this is a problem. So I know that this cannot be a fair test because I changed 2 variables. Now, even to make a further point, I went from granules to powder, and that's also not a fair test. I can't do this. Okay, so guys, if you want a fair test, that means that I can only change one variable from one experiment to the next. Okay, so I'm hoping that a couple of you got option C and explained yourselves properly. Okay, because I saw many weeks ago people just guessing and guessing. We're going to ignore you. We want the explanation because part of your job is to help each other, and that's the job of a mindsetter. We've got a couple of questions from those mindsetters, don't we, Indy?
Okay, we do. Let's have a look. I think we have a couple more since we last spoke as well.
Okay.
How do you determine the amount of energy needed to start a reaction from Chantal?
Very,
Huge
very
question.
difficult. Okay.
I thought
Now,
so.
a lot of learners say, okay, well, how do I guess this amount of energy? Okay, well, what I'm going to do is I'm going to draw you a nice graph here. And there we go. I think my line is almost straight there. Okay, we almost won that game. There we go. And what I'm going to plot for you is a profile of an exothermic or an endothermic reaction. Now, remember that if you take a look on one of these graphs, the grade 11s at the moment that have done this section are shouting to me, okay, that must be an exothermic reaction. There it is. I start and I begin at one level and I end at another one, and I find that I have changed my amount of energy. Remember that that change in energy was called delta H. But that doesn't answer my question. How much energy do I need to actually get this thing going? Okay, well, one of the things that I've got to look at on this graph is from the beginning, from my reactants, how far up must I go from the beginning? That is called my EA, or is called my activation energy. The energy of activation is the minimum amount of energy in that collision. They must smash into each other with the activation energy. That's how much energy they need to make something called the activated complex. They like to test this. Now, in the past paper that I actually looked at, they actually wanted you to know what an activated complex was. Now, some of the grade 11s are saying, okay, oh, I've got to remember all these words. Okay, now the activated complex is in between. So if I was to plot what was going on in the beginning, let's say I had something which was made of 2 particles that looked like that, and there was my reactants. If I start to take a look at the activated complex, what I'm going to do is I'm actually going to draw them in between. So these are my reactants. If I look at them in the middle, while they're busy reacting, they are actually joined together. Now that doesn't usually work. What you'll actually find is that they're all joined together. This guy is going to be my activated complex. My products are going to look very different. My products have now gone their separate ways. Let's actually label them. So here is my reactants. And so there's my reactants over there. And here are my products. The thing in between them is my activated complex. I need a whole bunch of energy usually to get that to happen because this is not natural. Sometimes it's drawn in square brackets. So I go in between there and out come my two products, and that's what's happening when I make my activation energy. I hope that answers that question.
I hope so too. Okay, let's go for one more question. It always happens when... Okay, hold on.
Okay. There was a question about a catalyst, wasn't there?
Yes, there was. Do you remember the question?
I think I do. So
I
somebody
think you
said,
do.
okay. Now,
I'll find the person, then I'll shout out the name. No.
okay, well, absolutely. Okay, well, I would just want to get that name mentioned. Okay.
Always.
Always want the shout out. Okay, so what I'm going to do is start to talk to you about what a catalyst does. Now, these catalysts, these chemicals which
I
help.
found the answer. It was Mac, and she says, does a catalyst increase or decrease the rate of reaction?
Absolutely. Okay, a catalyst always speeds up a reaction. Now, there is another chemical which slows down a reaction, but I'll talk to you about that in a moment. I'm going to talk to you about what a catalyst actually does. So if I look at that reaction rate as a result of this energy profile, this was my original exothermic graph. Now, we haven't got an x-axis, and my teacher's going to shout at me there. So let's put in my x-axis over there. This is my original reaction graph. I start out with lots of energy, I get the activation energy, and I go down to make my products. Okay, what does a catalyst actually do? Well, a catalyst is quite clever. A catalyst gives a shortcut for the chemicals. It says to the reactions or to the reactants, I've got a better way of doing this. So what you'll actually see is that the reactants allow for a lower activation energy. What I'm actually going to see is that when I've got a lower activation or energy of activation, that means I'm going to have a faster reaction. Because I require less energy, there will be more chemicals which meet the requirements. So a faster reaction is the result of a catalyst. Now, that dotted line over there is because of my friend, the catalyst. There we go. A catalyst is something which is going to speed it up. Now, there is another chemical which actually slows things down. Okay, now a catalyst always speeds things up. Let me keep that on the screen for anyone taking notes. There is another type of chemical. This is called an inhibitor. Now, an inhibitor is something that slows down a reaction. An inhibitor can be very, very helpful to us as well. A lot of the medicines and the drugs that we take to help diseases are actually called inhibitors. Now, an inhibitor is the opposite of a catalyst. This slows things down. So it slows down reactions. Now, inside my body, there's many reactions. When I cut myself, when I actually poke myself or cut myself, I don't do this on purpose, but when I cut myself, there's chemicals inside there which react with my nerves and they tell my brain that I'm in pain. So what do? I grab myself a painkiller like a Panado or a Grandpa, and that is an inhibitor. And what actually happens is an inhibitor is going to slow down the way that those chemicals move into my brain, and they actually change the way that I feel that cut. So it's going to slow down that pain chemical inside my body. Inhibitors can be my friend. Sometimes they can slow down a reaction very nicely, especially reactions which make me feel kind of ow. Okay, so I see you furiously typing away. Does this mean that there's more questions? I think we might have time for one really short one.
We do, and I want to ask Andelia's question because I said I would, but I think it's so fantastic because a lot of the mindsets are actually saying, are actually adding more to what she's saying and,
that's great.
And reconfirming that they are understanding. So guys, I think it's so awesome that you are putting onto the page relaying what Phil has told you so other mindsetters may see. I think that's really, really cool. Okay, so this question, Phil, is from Andile, and he has asked, if we can please explain this formula. There is a formula that states rate of reaction, which equals the amount of substance used, or produced
Okay.
divided by reaction time.
Okay, so divided by time. Okay, so right in the beginning of the lesson, I actually talked to you about this. If I can figure out how much of something that I'm actually making and how quickly I'm doing it, remember that we had 3 different ways of measuring the amount. So either I'm measuring the amount in terms of the mass lost. So these were those diagrams which were posted on the page. Take a look a little bit earlier, or the volume which was produced. And I measured this. This actually gives me the slope of those experiments. It gives me the slope of the graph. That was quite important. If you're watching a little bit early on the lesson, this equation actually gives me the slope of the graph. Okay, unfortunately, we're running a little bit short on time. I'm going to hop on that page and help you guys a little bit later. But
Yeah.
I think we've got to say goodbye for tonight.
Yeah, but that's okay, guys, because guys, please help each other out on the page. You know how it goes. Sometimes, we don't have enough time to answer all of your questions, else we would be here forever and ever. So that's why, to learn more and to learn extra, help each other out on the page, guys. I'm sure Phil will go on a bit later and answer some of your questions. If not, you can also email helpdesk@learnextra.co.za, and we are always, always behind the page. I just want to say, we will be posting the winners for the Casio and the Labeler tomorrow. Guys, can you believe that we've got something very exciting happening tomorrow? I think that we will reach our 2,000 mark. We're on 9,826. So from tonight, grade 12s, get everyone liking the Facebook page. Thanks for learning more and learning extra, grade 12s. You rock. Have an awesome evening. Good night. Goodbye. See you later. Bye.